So in this video, we're going to be looking at the second part of the energetics topic, which is taking what we know about enthalpy changes and applying them to Hess's law. So we're going to be looking at what Hess's law is, how we can use it to calculate enthalpy changes, how to construct Hess's cycles, and then being able to evaluate results of experiments, which we've done previously in the last video of energetics. Core Practical 2 is the determination of an enthalpy change of reaction using Hess's law, and there is a video on this on the Year 12 playlist on this YouTube channel. Feel free to check that out if you want to know how to carry out the core practicals. So the first thing that we're going to look at is standard enthalpy of formation. So as with the others, this is a definition that you have to know. And standard enthalpy of formation is the enthalpy change measured at standard conditions when 1 mole of any substance is formed from its elements in their standard states. For example, we can have graphite, or carbon in the form of graphite, reacting with oxygen as a gas to give us carbon dioxide gas. Or carbon in the form of graphite reacting with oxygen and hydrogen, both as gases, to give us liquid ethanol. Now, most of these enthalpy changes of formation cannot be determined experimentally, so we have to use a process known as Hess's law. Now, this can be quite tricky, and some people do find this quite tough, so we're going to go through what Hess's law is, and we're going to go through lots of examples. So again, a definition that you have to know. Hess's law states that the enthalpy change of a reaction is independent of the path taken in converting reactants to products, provided the initial and the final conditions are the same. So what does that actually mean? Well, this is basically saying we can go from A to B, or we can go from A to C to D and then to B, and the enthalpy change of pathway 1 is going to be the same as the enthalpy change of pathway 2. So these will all add up. So for example, if pathway 1 gave us an enthalpy change of 100 kilojoules per mole, pathway 2, going from A to C, C to D, and D to B, must also be 100 kilojoules per mole, and we can use that to our advantage. This is an application of the first law of thermodynamics, which is also known as the law of conservation of energy. So we cannot make or destroy energy, we can only transfer it. And we can use this in order to indirectly calculate the enthalpy change of formation for a substance or any other enthalpy change that cannot be measured directly. So an example is the formation of carbon monoxide. Now, we can't measure this because whenever we burn carbon, we are almost certainly always going to make carbon dioxide and we're going to get complete combustion. We cannot confirm or verify that the only product we get is carbon monoxide. So we can't actually carry this experiment out. But what we can do is we can use the enthalpy change of combustion for carbon and for carbon monoxide, and we can use Hess's law to do this. Now, there are 2 ways that we can do this. There is subtracting equations, or there is using a Hess's cycle. I will cover subtracting equations very briefly, but the one that comes up in exams is the use of a Hess's cycle. So what we do for any of these reactions is we write out our target equation. So we wanted to determine the enthalpy change of formation for carbon monoxide, and this is the target equation. We have carbon in the form of graphite reacting with half a mole of oxygen as a gas to give us carbon monoxide gas. We would then be given these 2 equations, or we would be told use the enthalpy of combustion and you can figure these equations out. Now, what we have to do, if we go back to these ones, which is what we had, we have to reverse the second equation. And the reason that we have to reverse the second equation is we want all of our reactants and all of our products to be able to cancel out and leave only the target equation. So if I reverse the top one, sorry, if I reverse the second equation, not the top one, the bottom one, I can then cancel out CO2 on both sides. And then I can cancel out half of this oxygen to leave me with half here. And then I have my products and I have my reactants. It's a bit messy, so I do apologise, but hopefully you can see that. And then because we have reversed the second equation, it was minus 283. When we reverse it, we change the sign and it becomes plus 283. So then we add these two, so plus 283 plus negative 394, and we get a combustion value of minus 111 kilojoules per mole. So our enthalpy of formation is minus 111 kilojoules per mole. So what we can also do with this particular reaction is we can construct a Hess's cycle. Now, a Hess's cycle is still using these same equations. We are just displaying them in a slightly different way. So remember, our target equation was this one here. And we were also looking at our enthalpy change of combustion for carbon and our enthalpy change of combustion for carbon monoxide. Okay. So when we're constructing this equation, this cycle, what we're looking to do is we're looking to show what can be reacting on each side and what they are then going to form. So these two arrows here and here are going to represent the two arrows in these equations. So what does that actually mean? Well, on the left-hand side, we're looking at graphite, and we said that when we burn graphite using an extra half mole of oxygen, we are going to form carbon dioxide. So I've just taken this same equation number one, and I have written it, instead of writing it horizontally, I've just written it at a slightly different angle. I then come over to the right-hand side, and I look at carbon monoxide. In my equation number two, I said I reacted that with a half mole of oxygen, and I'm going to form carbon dioxide. Notice that there is an overlap in the reactants and the products, and the products between these two reactions. That is the point in this Hess's cycle. So this is now my cycle, and I can add in my values here of which I said, and I'm going to call this side delta H1, and this side is delta H2. Now, Hess's law states that the overall enthalpy change is independent of the pathway that it is taken. So what we want to do is follow the arrows. And what we can see is the reaction that is represented by delta H1 is going to be the same as going from graphite and oxygen to carbon monoxide, then to the carbon dioxide. Therefore, delta H1 is the same as adding the enthalpy of formation plus delta H2, because we are simply following the arrows. All I then have to do is substitute my numbers in, which you can see I've done here, and then I rearrange in order to find delta H formation, and again I get a value of minus 111 kilojoules per mole. So in general terms, how do I write out this equation? Well, I start off with my component elements. I have my delta H formation, and I have the compound that I am forming. And then what I look at is the combustion. Now, this is when we're using enthalpy of combustion. I look at what are the products formed when I combust my elements, and what are the products formed when I combust my compounds. And you will see that there is an overlap every single time. And then all I do is I add up the sum of these combustions on both sides, and then I carry out my delta H. And it always works out to be, if I call this side delta H1 and delta H2, always get into the habit of doing that, it is saying that to work out the enthalpy of formation, I do delta H1 subtract delta H2. So let's go through some examples. I'll do some worked examples where everything is on the screen, and then we will do 3 or 4 examples where I go through it with you. So calculate the enthalpy change of formation of methanol given the enthalpy change of combustion for methanol, carbon, and hydrogen. So the first thing that we want to write out is our target equation, which is this one here. And that is the enthalpy of formation for methanol. So we're forming it from carbon, we're forming it from hydrogen, and from oxygen to make our product of CH3OH. So that's what we want to figure out. Now we look at the information that we've been given. You can see that we have been given the combustion enthalpy for our product, and we've also been given the enthalpy of combustion of 2 of our reactions. Now, they've not just given you these for fun, they have been given to you for a very, very specific reason. So then I look at, well, what is the formation? When I burn graphite, I'm going to make carbon dioxide. The carbon reacts with the oxygen. When I burn hydrogen, I'm going to make water. And I'm burning 2 moles of hydrogen, so I have to make 2 moles of water. Now, as you can see, we're going to burn ethanol on the right-hand side, and of course, that is going to make 1 mole of carbon dioxide and 2 moles of water. They overlap. That is the entire point in this topic. So then we look at the values. Well, I need to add 394 for my graphite, and 2 times my hydrogen, which is 286. And then that's going to, on the right-hand side, I'm going to have minus 726. So we've said that delta HF is going to be equal to delta H1 minus delta H2. So here is my delta H1, which is adding these 2 values together, and then I'm going to subtract delta H2, and I should get a final answer of minus 240. Now, I can also use Hess's law for other reactions that are not just combustion reactions or formation. I can look at the enthalpy of reaction for thermal decomposition, and this time, instead of using a combustion, I can use neutralization. Now, the process is entirely the same. There makes no change to what you should do. So we write out our target equation for the thermal decomposition of calcium carbonate, and we're going to make the calcium oxide plus CO2. Then we look at the equations that we've been given, and both equations we are reacting either our reactant or our product with 2HCl. And you can see there is an overlap. I'm going to make my salt, I'm going to make some water, and I'm going to make CO2 as well. So then I put that into my equation and I say, well, if I've got calcium carbonate, I'm going to react that with 2HCl, and I simply write the products. CaCl2 plus H2O plus CO2. I come over to the right-hand side and I'm reacting calcium oxide this time with 2HCl, and I'm forming the calcium chloride. I'm also forming water, and the CO2 here is actually one of my products. So I already have the CO2, I don't need to add that in any way. Then I've labelled delta H1 as minus 17 and delta H2 as minus 195. And to calculate my enthalpy change, I do delta H1, take away delta H2, I input the values, and I get plus 178 kilojoules per mole. And the last worked example is looking at the enthalpy of reaction for the hydration of anhydrous copper sulfate. Again, I'm given equations. So my target equation is this hydration. So taking the copper sulfate, adding 5 moles of water to give me my hydrated substance. I then look at what I have I've got my hydrated copper sulfate, and that's my product. So when I react that with water, I'm going to form these these 3 things, which go at the bottom. These are my products of the reaction on the right-hand side. Then I look at copper sulfate. When I react that with water, I'm going to form 2 of my other products, but of course the 5H2O appears as one of my reactants, which is why it's at the bottom. I then put in my delta H1 is 67, and delta H2 is 11.3, and of course delta HR is delta H1 minus delta H2, and I get a value of minus 78.3. So let's actually go through how we do this in practice. So let's look at one example here. So we want to use the standard enthalpy changes of combustion given in the table to find the enthalpy change of formation for ethanoic acid. Now here is my target equation for ethanoic acid, and I'm going to have to use my combustion of carbon, combustion of hydrogen, and combustion of ethanoic acid. So let's start to put this together, and let's take each thing one at a time. If I have the combustion of graphite, I know I'm going to have my arrows, of course, going to my products. So the combustion of graphite is going to give me carbon dioxide, because the combustion is that equation. But I have 2 moles, so I must be making 2 carbon dioxides, because I just simply multiply everything here by 2. When I combust hydrogen, I'm going to make water, and I react that with a half of oxygen. Again, I have 2 moles here, so I make that 2, that becomes 1, and I make 2 moles of water. So I've taken my two reactants, and I've shown how they react, and I do this by reacting with 2 moles of oxygen, which is here. When I come to the other side, if I take my CH3COOH and I react that with oxygen, I know I'm going to make CO2 and H2O. When I balance these, I'm going to make 2 and 2, and I need 2 moles of oxygen to do that. Notice that I'm making 2 CO2s and 2 H2Os, which are already my products that are at the bottom. So now I have my Hess's cycle. So delta H1 is going to be 2 times minus 394 and 2 times minus 286 added together. My delta H2 is going to be equal to minus 870. And we've said that delta HR is going to be delta H1 minus delta H2. So let's just substitute all of that in. I have 2 times 394 plus 2 times 286. That's my delta H1. I'm then going to subtract minus 870. I plug all of that into my calculator, and I should get a value of minus 490 kilojoules per mole. You get 1 mark for your correct cycle, 1 mark for showing that you double your carbon and your hydrogen enthalpies, and 1 mark for your final answer. And there you can see the final answer. So for worked example 2, we're looking at methane burning in a limited supply of oxygen to give us carbon monoxide and water. We cannot measure this directly, so we're going to have to use our enthalpy changes of combustion for methane and for carbon monoxide in order to work this out. So let's just recap very quickly. CH4 plus O2 is going to give you CO2 and H2O. Let's check our balancing, where we're going to make 2 waters, and I'm going to need 2 moles of oxygen. And if I have carbon monoxide, I have to react that with half a mole to give me carbon dioxide. Those are the equations for my enthalpy of combustion. I'm going to need them for my Hess's cycle. So we want to draw a Hess's cycle that will enable me to calculate the enthalpy change of combustion. Okay, so we start off with our target equation given to us, and we're going to look at what happens when we burn methane. So when I burn methane, I need 2 moles of oxygen. I already have 1.5 as one of my other reactants, so I need another half mole of oxygen, and I'm going to form just exactly what I've got there, CO2 gas and 2 H2O liquid. I then go over to the other side and I'm looking at how I burn carbon monoxide. Well, when I burn carbon monoxide, I'm going to need a half O2 and I'm going to make CO2, and the water you can see here is already one of the reactants, so that just transfers up. Then we have delta H1 is going to be equal to minus 890, and delta H2 is going to be equal to minus 283. So let's calculate the enthalpy change. Well, the enthalpy change of reaction is delta H1 minus delta H2. So we have negative 890 minus negative 283, and that gives me a value of negative 607 kilojoules per mole. And there you can see our Hess's cycle and the answer in our mark scheme. So let's look at a past paper question. This is from the January 2019 paper. Now remember, in the old specification, if you are using old spec past papers, these are all in Unit 1, because energetics used to be part of Unit 1. You will not find energetics questions in Unit 2. So the standard enthalpy change of formation for propan-1-ol cannot be measured directly. Complete the Hess's cycle below to calculate the standard enthalpy change of formation and add all of the missing enthalpy changes, arrows, and species. Okay, so we're going to have how we combust each of these reactions, and we're wanting to calculate our formation. Now notice that we have a slightly different Hess's cycle here. Our target equation that we've been given is not the formation equation, it is a combustion equation, but that's okay. We can still do our same process, we're just twisting it slightly. So let's think about this here. This is our propan-1-ol, and we want to measure its enthalpy of formation. So what is it formed from? Well, it's formed from some carbon, some hydrogen, and some oxygen. Now you can see in the box we're going to have 3 reactants here, and this is going to be our enthalpy of formation for propan-1-ol. Okay, so how does this form? Well, it forms from carbon as a solid, which is graphite. It forms from hydrogen as a gas, and it also forms from oxygen as a gas. Now we need to balance this out. So how many carbons do I need? Well, I need 3 carbons here. I need 4 hydrogens. And in terms of the oxygen, well, I only need 1 oxygen in my propanol, but you can see I also have 4.5 oxygens here. So I take this half of oxygen and I add it to the 4.5, and I need 5 oxygens. I've already been told that my carbon my enthalpy change of combustion for carbon is going to require 3 because I'm burning 3 moles of carbon to make 3 moles of carbon dioxide. Now I need to look at the water, and that's going to be another arrow upwards, and I need 4 times the enthalpy of combustion for hydrogen. So you get 1 mark for all of your correct elements. You get a second mark for the state symbols and the coefficients. And then you get a third mark for showing the enthalpy changes with the arrows. So now we need to have we have the completed cycle and we have the data, and we're going to use this to calculate the standard enthalpy of formation. So let's just go back real quick here. We said that we needed 3 of our carbon and we needed 4 of our hydrogen. Okay? So we're going to call we're saying that to go from the formation of from these elements at the bottom to our enthalpy of formation through our enthalpy of combustion of propanol is going to be the same as combusting these two. So what that actually means is going from here up to these products and then to these products is the same as going from here to there. So hopefully that makes a bit of sense. So in order for us to calculate our enthalpy of formation, we need to do, as you go back and you have a look, we need to take our enthalpy of combustion of carbon and add it to the enthalpy of combustion of hydrogen, and then we're going to subtract the enthalpy of combustion for propanol, delta H1 minus delta H2. These are delta H1, this is delta H2. So I've got 3 times minus 394. I add that to 4 times minus 286. And from all of that, I'm going to subtract minus 2021. I plug all of that into my calculator and I get an answer of minus 305 kilojoules per mole. Now this is a particularly tough question because it kind of throws on its side or on its head what we've been looking at. But if you can do a question like that, you can do any question. And you can see that we have our Hess cycle and our mark scheme, and we get an answer of minus 305 as we worked out. Now let's look at a slightly different question, and let's have a look at June 2017, and this time we're going to be using enthalpies of neutralization. So the first part is asking us to calculate Q, and then hence our enthalpy change. So Q, remember, was Cm delta T. C is 4.18. Our mass that we used is going to be 100 because we used 100 centimeters cubed of the water, hydrochloric acid, and my initial temperature was 21.5 and I went down to 14.25, so I have a value of 7.3. So Q is going to be 3.0514 kilojoules. I can then work out my number of moles of the sodium hydrogen carbonate, which would work out to be 0.095238. So delta H is going to be minus is going to be Q over N, which is 3.0514 divided by 0.095238. And we get an answer of positive, because we have a temperature decrease, positive 32.040 kilojoules per mole. Okay, and this is the enthalpy change of reaction 2. So reaction 2 is plus 32.040. We are then given reaction 3 to be minus 36.3 kilojoules per mole. And now we want to be able to calculate reaction 1 using a Hess cycle. So we're going to need these two equations here. So my target equation is already given to me. That is reaction 1. So now I need to look at, well, if I have sodium hydrogen carbonate, I go to reaction 2, and I can see when I react that with hydrochloric acid, I'm going to make NaCl aqueous. I'm going to make water, liquid, and I'm going to make CO2 gas. Now notice in our reaction 2, we only have 1 mole, but here we have 2, so I have to put a 2 in front of everything here and just scale it up. And this is my first arrow. I achieved this reaction by reacting it with 2 hydrochloric acids. So delta H1 is going to be equal to 2 times our reaction, which was 32.040. I then look at the right-hand side, and I know that I've got sodium carbonate. I look at sodium carbonate reaction, which is reaction 3. It reacts with 2 HCl, and I make 2 NaCl plus 1 water and 1 carbon dioxide. And the 1 water and 1 carbon dioxide are already here, so they add to this reaction to give me 2 moles of each. So this is delta H2, which we've been told is minus 36.3. So my enthalpy change for reaction 1 is going to be delta H1 minus delta H2. So that's 2 times 32.040 subtract minus 36.3, and I get a final answer of 100.3. It is a positive answer, and my unit is kilojoules per mole. So there's your mark scheme showing your calculated Q, your Hess's cycle, and also your final answer of 100.3. So I hope that's made a bit more sense about how to do Hess's law calculations using Hess's cycle. I won't lie, this is one of the toughest topics that you face in AS level chemistry. It can be very difficult to grasp. The best thing that you can do is practice. You will find lots and lots of past paper questions available on the internet, and you can also find past paper questions on Unit 1 papers. Remember, Unit 1 for the old spec for energetics, and you will be able to have the mark schemes and be able to try out all of these. The best way to get better at these is to practice. If you're still not sure, please make sure to leave a comment below and ask any questions, and I'll do my best to answer them. Hopefully it's made a little bit more sense, and we hope to see you back on the channel soon for any other revision videos you might find useful.